Hello, friends. How are you all today? Have you ever wondered what operating system is and how it is going to work? It's coming up right now. I'm Prashant, a technical trainer and freelancer from Dharani Academy of Technical Education, Bengaluru. Let's start with the concepts of operating systems.
In the last class, we were looking at why we need the virtual memory. What is the reason behind the requirement of a virtual memory? And we discussed when we are able to allocate the memory in such a way that we don't load the whole program onto the physical memory of the computer. We load it, right, a part by part. So there has to be a new memory management software or a program that is needed, and when that is available, we can create the new space of address called virtual address space, and we can link that with the physical memory. So there will be a memory mapping happening here as well. uh, At the same time, this mapping is not the same mapping as the logical address, which was one-to-one and a finite space. So here, the expectation is that we can we are expecting a huge amount of memory, right? It should look like we have a very huge amount of memory available, and we call that as a virtual memory. Okay, so this was the recap of the previous class. Now we'll go for a diagram showing that the virtual memory and the real physical memory, how this happens. Okay, so okay, this is the one which we require for virtual memory. Then the memory mapping function, let's say the finite memory mapping function will be represented over here. Then we are expecting a physical memory is not exactly same as that of what you call the virtual memory. I'm supposed to write a smaller one, so let's use a smaller one here. This is the physical memory. Okay, and then let us write a maybe a cylindrical structure here. And okay, all right, now let's finish this. Okay, now the memory organization is in this way. So the leftmost one is considered as the virtual memory space. Let's say this is virtual memory, where each location, right, is not called not like the physical memory. We have a different name for that. It is called as a page. This is page number 0. This is the page number 1. It's like a page. Okay, then we have page number 2, dot dot dot. Like that we have several pages available, and let's write the last one. So let's call this is page number V. That is a virtual memory. Now you have a mapping function, right? That is decided by the program itself, which is going to be used for the memory management, virtual memory management of the computer. So we'll not anything, will not write anything inside this. We'll simply write a memory map. Okay, this memory map will directly map this into the the physical memory. So virtual memories, you can get some arrows like this that will convert this into the that will convert the virtual address into a physical address. So this has to be the physical memory. So this is finite. Again, you are going to have known number of spaces over here, right? Now why we have written something like a cylinder over here? This is actually representing the actual the memory cells, okay, of a computer, right? Inside the memory you have what is called as a memory cell, right? Made up of maybe a transistor, right, FET, or even the capacitors. Using physical uh, components, you have the cells. So each one location is actually one cell. That's why we just wanted to show that's what is happening, right? That's why we are writing like this. So this is the physical memory, right? This could be like a hardware cells. So this is how the virtually created space is linked to the physical memory by using the memory map. So virtual memory makes the task of a programming, right, that becomes very easy. Now you don't have to worry about the amount of physical memory available, and we can always concentrate on the problem to be programmed than worrying about the physical constraint. How much memory I have, will my program run or not? These things the programmer has nothing to do with it. Okay, so after this diagram, now we'll write that point. This is the virtual memory makes the task of programming tasks of programming much easier. Okay, so this is because I will justify, uh, because the programmer because the programmer no longer programmer no longer needs to worry about the availability of the physical memory, right? And definitely when this problem is ruled out, actual problem that needs to be solved by using a programming that can be concentrated by the user. That's the benefit to the user. Now, so we already have used a word called virtual address space. Okay, so let's talk about the virtual address space, right? Whenever we are defining a virtual memory, there will be a virtual address space, right? Corresponding to any process that runs in the OS, we try to give a virtual address space. This basically refers to, right, the virtual view, how the process is being stored in the memory. We'll go for another diagram later just to visualize this, but let's write that point now. Okay, so the the virtual address space of a process refers to uh, the virtual view of how a process is stored in the memory. Okay, so this view of a process has a certain address, say maybe address 0. Okay, and it exists in the continuous memory, right, till some location. Okay, it can normally include the stack part or any other part. Okay, so let's try to write a simple diagram for that. That is the virtual address space. What exactly is the virtual address space? So we have, let's say, some space, and maybe one part is stack. It starts at some location, and normally we will have some other spaces allocated. Maybe this is a heat memory, or you can also have the some part of this is allocated for data, followed by maybe some other space is allocated for the code, actual code of the what we are loading, etc. Like this, we may have several space available. Let's write the exact names here. So this is the location for maybe address 0. Okay, this is the maximum address, maximum, right? So address, I'll write this is address 0 to address maximum. So we have the in the memory we have to store the code. We have space for data. We have a memory called heap. We have empty space, maybe just let's indicate like this. Then you also need what is called as a stack, right? So the total virtual address space can have any of these. Okay, so this whole address what we have here is referred to as the virtual address space. So physical memory may be organized in the page frames, and the physical page frames assigned to a process is not continuous when it comes to the physical address. Physical memory you cannot allocate continuously because, right, of the practical restrictions. Some part will be occupied, some other part will not be occupied. Whichever is not occupied, you will allocate that to a process. So it becomes very difficult for a some pointer to point it out whenever the execution takes place. All right, so because of that, what we are doing, we extended that to a logical address, but it had its own drawbacks. So we are going for the virtual address space. Okay, so we need to recall the paging process, in the sense how the memory blocks are allocated to a process in case of in case of the physical memory. Okay, now what happens in this diagram, we'll talk about that now, right? So here we can see the arrow marks are actually showing the empty space, and we can see one thing, that is there are two parts, one which are allowed to grow, in the sense one is a stack, right? The arrow mark which is shown top to bottom is the growing of stack will move downwards as you fill data to the stack. Okay, at the same time there is another memory block which is called as a heap memory, and it is shown here that this heap memory grows upwards. Correct, so we can see that, right, there is a arrow mark for heap. All right, let's write that point here, because that's the we are discussing about the virtual address space now, and we will mention all the characteristics. Okay, so that is uh, the heap is allowed to grow upwards in the memory in the memory as it is allowed to sorry, as it is let's write in this way, as it is used as it is used for the dynamic memory allocation. So since it is, we are allowing, right, dynamically allocating the memory, right, we have to allow it to grow some, in some sense. So for heap memory we are allowing it to grow upwards. Similarly, we allow the stack to grow down, because one moves upwards, other one has to move downward. Both of them we cannot fix the size. Okay, so we'll write about the stack as well. The stack is allowed to grow downwards. Okay, uh, right, but we know that in order to allocate the stack, read the stack, write the stack, we need some functions. So we'll write that downward uh, through the function calls. right. So there is a space, blank space between the heap and the stack. Okay, right, that's actually the empty space what we see in the diagram, and that is also a part of the virtual address space itself, right? Because that is empty, that's all, right? It doesn't mean that, right, we are not exactly using it. It doesn't mean that we are not using it, we are using it. Okay, but that blank space will require actual physical pages only if heap or stack grows, right? In the sense, if at all you are exceeding this space, you need what is called as the physical pages to be present, right? Otherwise you can store here. Okay, let's write that here. The blank space between heap and stack is also virtual address, that is also corresponding to the virtual address space. So virtual address space includes, right, there is what is called as this empty space. These empty spaces are actually referred as the sparse address space. So sparse address space is very useful because the empty space can be filled as the stack or heap segments grow, right? We can allocate that in an automatic fashion. That is also supported, right? Everything is a part of the software which we write to support this virtual memory, right? Whichever software we use, all these are the uh, features to be included in that software, right? So we just mentioned what are the various features available with respect to the virtual memory. Okay, so next we write, so the empty space is actually called as holes when it comes to the technical terms. Okay, so we'll write the same term here, the virtual address space that includes empty space called holes are are known as the sparse, S-P-A-R-S-E, sparse address spaces, right? So sparse addressing is something like, so when we use the sparse addressing, there is an advantage. The advantage is like you can fill the holes, in the sense whichever space that is empty, right, by using a stack, by using a heap, or you can allocate dynamically. So the advantage is that. So advantage of using sparse addressing is that we can use either the heap or the stack, okay, to fill data, or the other option is that we can use the dynamic addressing or dynamically allocating the memory to fill the data. This is possible. Okay. Now we understood that the virtual memory is a concept which separates the logical memory from the physical memory, right? And the virtual memory also allows the files and memory to be shared by two or more processes using what is called as a paging. So this is the new concept coming up. So because of the paging of the page sharing concept, we have certain advantages. We'll see them now. Okay, so the next point we are going to write here is the virtual memory allows uh, files and the memory to be shared by two or more processes through the page sharing. Okay, with the following benefits. So we'll look at the benefits now, right? What are the different benefits? The first one is whenever we have a system, it has its own functions called as library functions. They are stored in systems library. Okay, these system libraries can be shared by several processes by simply using a mapping function. Okay, mapping function shared by the virtual address space, which share the basically the addresses of these libraries will be shared through the address space of the virtual memory, right? Each process normally considers shared libraries to be a part of, right, virtual address space, and the actual page of the library will be present in the physical memory. Okay, so library is mapped to read-only space normally, because library function should not be altered by the processes. Then there will be a lot of problems if a library function is altered by some process. Okay, so normally the ROM part is a physical memory address, right? ROM is physical address. Normally the system's libraries will be present in the ROM, but it for all the processes it looks like it is present in the shared space of the virtual memory. That's first advantage, right? So system, this is the point number one. We can write system libraries can be shared by several processes through the mapping of uh, shared object. You create an object which is getting shared uh, into the virtual address space. Okay, so in the sense, this means that for the processes which use the system's library functions, right, they're going to see that, okay, the system libraries are present on virtual address space, but actually you use a mapping function that links the system library functions to the physical memory. It's actually present on the physical memory. Now you see that all the system library functions are not necessary, right? A process is running and it requires the function, certain function from the library, means only that function can be loaded to the physical to the physical memory, and then you can see that it's actually running. Okay, so that's the idea here. So one more thing we need to remember here is that, anyway, we are not going to write that, but it is important that we remember that. Okay, a library is mapped to the read only part of the actual memory, ROM only. It will be present in the ROM. Okay, that's the first point. Then let's write point number two. Point number two, the virtual memory enables the processes to share the memory, right? So processes can also share the memory. In the previous class, we saw that I might had a limited 500 MB space available. If you load the whole complete program or complete process onto that location, maybe all the complete 500 MB is loaded, right? No more space left over. What you do now, you create a virtual space, right, and share part by part. So what happens, only 100 MB is filled now, because virtual memory holds this complete process, but we are loading only the required part of the code that, right, should be running at the given point of time to the physical memory. That makes sure that only 100 MB is filled, 400 MB is left over. So out of this 400 MB you can, right, run other processes as well. Correct. So this was the point we discussed, so we'll write that now. So the memory virtual memory enables processes to share the memory. Okay, two or more processes, right, can run, right, simultaneously in a easier fashion compared to the normal uh, way of running the code. In addition to that, this is important. Why we are supposed to make sure that multiple processes run concurrently by sharing the memory? It is because, right, we expect whenever there are multiple processes running in the background of an OS, right, there may be a communication required between the processes, so it requires shared memory. So you have to make space for shared memory. So whenever multiple processes run parallelly, they have to communicate with each other through the shared memory itself. So we have to have the shared memory. That's the point to be remembered when we say that virtual memory enables to share the memory. Why it is required? Because they have to communicate, right? One process creates a variable, and that value of the variable should be passed to another process, let's say. Okay, in that case, you see, the shared memory comes into picture. Also, the virtual memory allows one process to create, right, a specific region of memory that can be shared with multiple processes. It's something like you have a variable, right? Value of the variable has been updated by you, in a sense, one particular process, and that value needs to be, right, used by multiple other processes running. Okay, so that also requires the same concept, which is shared memory. Sharing a variable with any one process, or sharing a memory or a region of memory with multiple processes, right, requires share the memory. That's why this point is very important. Okay, the process sharing the region of their what you call memory, right, if it is present on the virtual address space, right? Normally what happens, you are actually sharing the physical address only, but since you wanted the continuous uh, addressing to be present, right, for a huge data present over there, right, the virtual address becomes very handy. Okay, all right, so that's the importance of point number 2. Let's go to the third point here. This is point number 3. The virtual memory can allow the pages to be shared during the process creation, okay, just to increase the speed of creation of a process, because process creation normally takes some time in the OS. You can speed up things by using the virtual memory. So that point is what we are going to write now. So this is the virtual memory. The virtual memory can allow uh, the pages to be shared during a process creation, right? And there is a function allocated for that, so I'll write the name of the function with the fork. This is a function, we'll see that later. Function the called fork system call. It's a system call, right? The basic, one of the most basic function executed by the OS is called as a system call. Okay, comma, we can write speeding up the process creation. So the process creation can be, right, made faster using this. So just to understand all this, the complete concept of these 3 points, right, we'll write another diagram over here. Okay, so this diagram corresponds to the points we discussed now. So one memory, and we have all right, this is the second one, which is the, maybe it is actual memory, right? We have the virtual memory space, we can have multiple virtual memories as well, right? So at the center, let's say we have certain shared pages. Okay, so we know that on one side we can have the stack. Okay, and somewhere at the center this stack and the okay, I can also write the heap. Below that I have the data and the code. So we know that this is growing in this fashion, this is going in this fashion, and let us say somewhere at the center I declare and I use the shared library. So this is the virtual memory, right, corresponding to a process 1, say first process. Okay, this is, I can call it as maybe the process P1. Similarly, I have another process P2 that is also, right, using its own virtual address space. So which means I'm going to have the same things over there. There will be a stack associated with that which grows downwards. Somewhere at the center, I'm allocating the memory required for the shared library, right? It looks like, okay, the particular shared library is present inside its own uh, address. Okay, but the address is virtual. All right, then So there will be heap, there is data, and there is code. Okay, but what exactly is happening here is it is actually sharing this space itself. Okay, the shared library is actually the only one thing which is present in the physical. Okay, so they are called as the shared pages. Okay, so the next concept is that uh, we try to implement the virtual memory. So how do you implement this is what is coming up now, and that concept is called as demand paging. Okay, we go to demand paging where we understand how to create the virtual memory. So next side heading will be demand paging. Right. So let's say that there is a executable program. We have written a program which can be executed by the computer. Right. Now let us say that it is loaded from the computer's hard disk to the memory of the computer, okay, which could be the RAM, where the CPU takes out the data required for the execution of any process. Now if this is a requirement, my there is an executable program in my computer's maybe hard disk, and it is getting loaded into the RAM, whenever you want this to be executed by the computer. This is the first part. Now one of the option is to load the entire program in the what you can call the hard disk, right? Entire program which is present over there can be loaded in the physical memory, say RAM. I can completely load it and execute. Okay, whenever you are executing that, you can do that. That's the first option, right? But what is the problem with that? We may not initially need the complete program to be present in the memory, right? So something like we can consider a program that starts with the list of variables, and there may be some options that you can select, right? Only after that the program comes into picture, right? The whole program comes into picture, because initially you don't need that, because you are simply loading some variables, creating some variables, data types. You are defining the structures, are you using class, etc. You keep defining them. Or maybe if it is a C program, maybe we define the user defined functions at the beginning. You see that they are not going to be running directly, they are simply being defined at the beginning, right? Only when it comes to the main program, right, then it is expected that you load, right, whichever part that's going to be executed, and take the exact functions which you are calling, you can load them, then you can run the code part by part. Right. But loading the entire program into the memory results in loading the executable code with all the options, right? Because maybe there are some conditions like a switch case statement, right? If you have a switch, you look at the value and then go to that specific case and execute. But if you load the whole program, what happens? You are actually loading the complete program uh, with all the cases present for a switch onto the memory. Okay, so all options you are trying to load whenever you go for the complete loading of the program to the memory, right? Whether an option is really selected by the user or it is not, we don't consider we completely store. Okay, so So what is the complete loading of the program? That was the first option. Whenever you want to execute, right, a program to be loaded to the memory of the computer. That's the first part. We will not discuss that because that's the normal way. We'll go to the alternative strategy, the second one. Okay, here our idea is that we initially load the pages. Uh, we'll try to load the pages only as they are needed, right? So demand paging is that. Demand paging, okay, I can write in this way. Demand paging is a strategy uh, to load the pages. Load the pages only as they are needed. Okay, so this is what is called as the demand paging, right? And it is a very common technique in virtual memory system because virtual memory is expecting the same thing, right? We want to load uh, the part of the program into the computer's memory only when it is required, right? So if you have a demand paged virtual memory, pages are only loaded when they are demanded during the program execution, and pages that are never accessed therefore will never be loaded into the physical memory, saving a lot of memory space, right, in real. So we'll write that point as well. With the demand paging, demand paging virtual memory, uh, we can say that the pages are only loaded when they are demanded during program's execution. Okay, so this is something like you are saving the memories that should be allocated for user defined functions. Whenever that particular function is called by the program, you load that function to the memory and you run that, otherwise you never load it. So, right, this means the pages which are never accessed are not going to be loaded, right? So therefore the pages that are never accessed are thus never loaded into the physical memory. Okay, now, so how this demand paging works? Okay, so we have the memory of a computer that normally gets accessed by using a technique called as swapping, right? Swapping in the sense, whenever you put something, whenever you have a program that needs to be loaded to the memory, it's called as a, right, swapping out, right, from the virtual memory. So you have the virtual memory, and from the virtual memory, right, we are swapping it out. That's the one thing. It's normal for the uh, operations that includes no virtual memory as well. So I have, we'll draw a diagram to understand this, but let's write the point now. So that is uh, the demand paging system is using what is called as a swapping, is using swapping, right? Where in swapping what happens, processes reside in normally the secondary memory, right? Normally the complete process what you want to run, or what we are going to call, they will be kept in the secondary memory such as the hard disk. Okay, but as and when you want that to be executed, right, you will put it into the RAM, or maybe the registers of computer of the CPU, or something somewhere like that. Okay, so we'll write this the swapping where the processes reside in the secondary memory. Right. So whenever we want to execute a process, we swap it into the memory. Okay, there is a main memory and there is the hard disk space. From the hard disk, you load it into the main memory whenever you want to execute that. This is the first thing. Okay, and once the program is loaded and it gets executed, and then you put that particular program or the process back to the hard disk, right? Otherwise your RAM will get overloaded, and we know that the space in RAM is very like limited. You put limit on whatever you can execute through the RAM. That's why, right, we use the paging system in virtual memory space, and that will be created in the hard disk itself. Okay, so let's write that point now. If we want to execute a process, if we want to execute a process, then we swap it into the main memory of the computer, right? Again here, the idea is that we are not going to swap the entire process to the main memory. Okay, we'll do part by part, right? Whichever that is expected to run, right, immediately next, only that maybe 3 or 4 lines of the code will come to the main memory. As and when it get executed, you put that code back to the original place and load the next 4 lines or something, right? This is called as a lazy swapper technique. So lazy swapper never swaps the page into the memory unless the page is actually needed. So lazy concept is that unless and until it is very much necessary, you don't do that, right? So that's why. So the next point is that uh, rather than swapping the entire process into the memory, into the memory, right? We use what is called as a lazy swapper. So the idea behind lazy swapper is that we use a lazy swapper which never swaps a page into the memory unless that page will be needed by the computer's CPU for execution. Until and unless that is needed, right, it will not be loaded. So that loader is referred to as the lazy swapper.
That's all for today. Let's resume the concepts in the upcoming classes. If you have any doubts related to the topics we discussed, please feel free to contact me anytime. Thanks for watching. Have a nice day. Goodbye.